Hey guys, the objectives of today's video is to introduce you to Mohr circle, as well as to derive a couple of equations for Mohr circle which will allow us to evaluate stress in different planes. So the Mohr circle allows us to analyze multi-dimensional loading on a soil. The strength of a soil is generally taken to be the maximum stress the soil can withstand before the deformations become unacceptably large. And in geotechnical engineering, we are generally concerned with the shear strength of soils, because in most problems in foundations and earthwork engineering, the failure tends to result from excessively applied shear stress. So before I derive the equations for Mohr circle, I'll just run you quickly through the sign conventions which are used. So normal stresses, these are stresses which are applied perpendicularly to a soil surface. We take compression to be positive. And for shear stresses, these are stresses which are applied parallel to the surface of a soil. We take anti-clockwise to be positive. And if I was to demonstrate that quickly in a diagram, say this is our soil element here. So this is our normal stress, which is applied in compression, so as a result this is positive. And shear stress, this shear stress direction, it causes the soil element to tend to want to rotate anti-clockwise, so as a result this is positive. We also have rotational equilibrium, which requires that pairs of shear stresses either point towards a corner or away from it. And I'll just quickly draw what that looks like. So say we have another soil element. So the shear stresses have to either point towards a corner or away from it like this. So let's now derive the Mohr circle expressions for the soil element that we have here. So as you can see here, we have our horizontal and vertical axis, and I'll just put in the stresses that we have here. So we have our shear stress here. I'll just call it XZ. And another shear stress. And we also have our normal stresses. So I'll call that sigma X. Let's call this sigma Z. Now we're interested in the shear stress and normal stress which are acting on this plane here, which acts at an angle of theta above the horizontal axis. So I'll just label these corners as well, A, B and O. So we can take the magnitude of AB to be of unit length. So as a result, this is a right angle here. So using trigonometry, we know that AO equals to the length of AB multiplied by cosine theta. And similarly, the length BO is equal to the length AB multiplied by sine theta. We can also assume unit depth going into the page. So let's now take equilibrium of forces. And let's first look at the plane that is acting perpendicularly to the wedge. So we'll consider normal forces. So before I write out my equilibrium equation, I'll just quickly write out the components of these stresses here. So we're going to be looking at the plane in this direction. So this works out to be sigma x cosine theta. This works out to be sigma x sine theta. So this is a right angle triangle, and this angle is theta. This works out to be sigma z cosine theta. And this stress here works out to be sigma z sine theta. So also the shear stresses. So this works out to be tau x z cosine theta. And this component here I'll just write over here, tau x z sine theta. And finally we have this one here. So this works out, this component here is tau x z cosine theta. And that component there, tau x z sine theta. Alright, so now we're interested in forces acting in the normal direction. So on the plane acting perpendicularly to the wedge, so the normal plane. And because we are evaluating forces, we have to multiply these stresses by the area which they're acting on. So just move this down a bit. Okay, so sigma n, that's acting on the area AB multiplied by 1 because unit depth, so I'll just write that as AB equals to, so all the forces that are acting in the opposite direction now to balance out the normal force, so sigma x BO sine theta plus sigma z AO cosine theta plus tau xz BO cosine theta plus tau xz AO sine theta. And because we know AO equals AB cosine theta and BO equals AB sine theta, we can substitute these expressions into this expression here to convert all the lengths into AB. So substituting BO and AO, sorry, that should be B here. We then get, so sigma AB equals to sigma x AB sine squared theta plus sigma z AB cosine squared theta plus tau xz AB sine theta cosine theta. So that's this term and then the second term here, so plus again tau xz AB sine theta cosine theta. Now of course we can cancel out all the AB lengths here. We can also add these two terms together. So just to simplify that down a bit, I'll write that again a bit neater. So the normal stress equals to sigma x sine squared theta plus sigma z cosine squared theta plus 2 tau x z sine theta cosine theta. Now there's a couple of trigonometric relations we can use in order to change this expression around. So So sine squared theta can be rewritten as 1 minus cosine 2 theta over 2. And cosine squared theta can be rewritten as 1 plus cosine 2 theta over 2. And also 2 sine theta, cosine theta can be rewritten as sine 2 theta. So substituting these relations into this expression above here, it becomes, so normal stress equals sigma x 1 minus cosine 2 theta over 2 plus sigma z 1 plus cosine 2 theta over 2 plus tau xz sine 2 theta. And I can just quickly expand this, so sigma x minus sigma x cosine 2 theta, all of that's divided by 2, plus sigma z plus sigma z cosine of 2 theta divided by 2, plus, and this term stays the same. Finally, we can tidy this up a bit. So the normal stress equals to sigma x plus sigma z divided by 2 plus sigma z minus sigma x divided by 2 multiplied by cosine 2 theta plus tau xz sine 2 theta. So essentially what this equation does, it relates normal stress acting on a plane of theta, and it relates this stress also to the horizontal and vertical stresses and shear stresses. Now if we were to perform a similar analysis on the plane acting parallel to the wedge, so just to go back to our diagram, so we're now interested in this direction, so we would be adding up this force, this force, this force, this force, this force, as well as that force. Okay. Now I'm not going to do the derivation again for the shear stress, but you should end up with this expression. So the shear stress acting on the plane that we're interested in, acting at an angle of theta above the horizontal, it'll equal to, so sigma z minus sigma x divided by 2 multiplied by sine 2 theta minus tau xz of cosine 2 theta. And if we square and add these two expressions together, we can determine that the radius of the Mohr circle will be the difference between the horizontal and vertical stress divided by 2. And the coordinates of the center of the Mohr circle can be found by the average between the horizontal and vertical stress. And that's it for today's video. Hope this helps, guys.